Hey everyone, welcome to Lecture 6 for Software Engineering Principles for Complex Systems, TDA 594. Now, as you may have noticed, today's lecture is a little different. There's a career fair today, which I hope all of you are aware of and are attending, and instead of our normal lecture, we're going to have this video lecture instead. Now, as always, I'm happy to take your questions. If you have any, you can email me, or we can just talk during the next class. Okay, so let's begin. Today, our focus is on variability implementation through design patterns. Now, I'm sure you have talked about design patterns in a previous class, right? These are descriptions of how objects collaborate in the code and how those objects are designed to solve a general design problem in a particular context. They're essentially recipes for implementing certain forms of behavior in a system. They are a classic object-oriented design technique and have a major place here as one of the easiest ways to implement change and variation in a system, implement reusable assets in a seamless and extendable way to allow your system to evolve over time by slotting in new features and controlling how the system evolves. I'm sure you've discussed design patterns before, so part of today will be review, but our goal is to highlight 6 particular patterns, some very simple, some more complex, that are particularly suited to implementing variable and evolving systems. Design patterns are one of our major means of language-based implementation. They operate at load or runtime within our code, and they are implemented through language mechanisms rather than external tools, and our features are encapsulated in the code as distinct units that we merge together through composition rather than having code for multiple features mixed in the same place as we would for, say, preprocessors. Okay, so let's start by going back to our object-oriented principles. We're implementing all these robots. We've got this whole product line of different mobile robots. So anyway, we want to implement several different robots, and robots can do things. They can target, they can shoot, they can move. So it seems reasonable that you might want to use inheritance so that you can add dozens of robot types and just inherit those common attributes and operations from the parent, with maybe a few new operations on the top. Okay, so all of our base robots, they can shoot, they can target, they can move. Then we have an abstract method called display that is concretely implemented by each individual robot. And we've got a couple of robots already. We've got a tank and a dog. Is this a great design? Is this something that could maybe get us in trouble somewhere, or are we done? Can we go home? Well, using inheritance is a good start. It gives you some good reuse of code. Right? We can write shoot, we can write target, we can write move once in the parent. Children inherit those. If they need to, they can override. But in general, we've implemented our code in one place and reused it, which is a good start. But this can start to get us into trouble as we change the system later. So what if we start adding new robots? And what if we add a drone? Well, a drone can shoot and target things in the same way that a tank or a dog robot could. But arguably, its movement is very different. Our tank, our dog, they walk along the ground. They essentially move in a 2D plane. They can move left, right, forwards, backwards. But drones now operate in a 3D space. They can also go up or down. So something's going to need to change in that code, right? And so our base option is to override the method in the child that we've inherited with our own version. It's a useful trick, right? Inherit these methods, but the behavior isn't the same, so we override it with our own local version of moving in the drone. Now, that's not bad, right? But if we keep doing this, this gets a little iffier. Let's say we've added our robot submarine, and our robot submarine has no gun. It just explores the water. It maybe has a little robot arm, so it can interact with something, right? It can target something, but it doesn't shoot. It just grabs things with the arm, right? And again, it moves in the 3D space like a drone. It can also move up and down. All right, maybe it still makes sense to group it with our other robots. It still targets. It still might have some other shared data attributes or other operations we're not showing here. But we're starting to reach a bit of a breaking point with these behavior overrides. It defeats the point of inheritance. Why inherit behaviors if you're not really going to use them as often? If they're not truly shared? The point of inheritance is to localize functionality so that to the parent, so that the change in one place changes it everywhere. It isn't much use if we just override everything. Okay? Now, another option we could consider instead is using interfaces, such as a Java interface. And here we're not implementing any code, or we're not implementing shared behaviors, but we're defining a contract that says that anything that implements the interface will at least offer this a set of known methods with known parameters. We're making a contract that we offer these functions. Okay, so we could define interfaces for some of these behaviors. Anything that implements the moving interface can move. Anything that implements the shooting interface can shoot. Okay, so we've moved out moving and shooting as their own interfaces, and now we implement our bots. And the robots all inherit target still from the base parent class, and they all implement display. And now some of them move and some of them shoot and some of them do both. So when appropriate, they implement the right interfaces. Our drone, for instance, is going to offer a move method. Our underwater robot offers a move method. Only drone offers a shoot. Underwater robot doesn't. And this provides assurances that if an object can move or shoot, we know how to call that behavior, right? That's a good start. This still isn't quite the full answer, though. We now know that if a robot can move, if a robot can shoot, it offers certain names for those methods. We know how to call them, okay? However, a big point of inheritance is the idea that we don't need to implement the code in multiple places. And if that code changes, we change it once. With just an interface, we have to implement the same behaviors multiple times. So our, you can see some ducks in this slide, right? I changed this example from ducks to robot at some point. So let's pretend here it's our tank robot and our dog robot is what that should be. And both of those have to implement the same move and the same shoot behaviors. And that's not necessarily good. So if we have to make a change, we have to change it in every spot it appears. And that's going to cause nightmares for maintenance. That's going to cause nightmares for bug fixes. Okay, so not the full answer yet. So how do we fix this mess? Well, let's ignore some of these fancy tools for a second. Ignore inheritance, ignore interfaces. Let's focus on the core reason these tools exist. And one of the big advantages of object-oriented design is that we can think of a system as a bunch of independent blocks that connect together. So let's do that. Let's identify what changes and isolate that from what doesn't. Right? So we have robots. What never changes about them? Let's take that and put that into our base robot class. Basis for all the other robots. Now, what does change between these variants, between these different concrete robots? Well, for one thing, we've seen how they move, or don't move, or fly, and so on. So let's separate what never changes about the robots, so targeting, appearance, from changing behaviors, from shooting, from moving. And so later we can alter or extend the parts that might change. Those are our assets in our product line without affecting the parts that never change. Okay, so we want to separate what never changes from what does. Our first inclination might be to do something like this, right? We create children, we program in moving and shooting when needed, implementing whatever behavior we need independently of the parent. This isn't quite what we want. This means that when we want a robot to move, what we need to know is what robot we're working with and how to call the right method, right? We need to know it's a drone and we need to know it offers this move with wings method. That's not great. What if we want to design code that could work with any robot? That doesn't really work because we have to know the specific robot. So this isn't really what we want yet. Okay, so now, of course, we could go back to stating the robot has move and shoot methods and override them. This is better. We know that all robots have the same methods, so we don't need to know which robot we're working with. We can just program saying, hey, we have a robot and a robot can move. Okay, that's better. We know all robots have the same method, so we don't need to know which robot we're working with. We can call the move method, we get the appropriate behavior. But as we've talked about earlier, this isn't great either because we need to re-implement the same behavior multiple times. So there's still an important lesson here, which is programming to an interface rather than an implementation. Even if the result varies, we always want to offer the same way to access a function of our robot or whatever it is we're building. Okay? I'll offer that assurance, and no matter what type of robot we have, if we call move, if we call shoot, we get the right result. So how do we do this right? Okay. What we want to do is take those moving behaviors, those shooting behaviors, and program them once. How we should do this is give them each their own class, and since the behavior varies, we don't want to inherit, but we can create an interface that says that any type of moving behavior will be implemented through a method called move. Any type of shooting behavior will be implemented through a method called shoot. We provide a contract. Here is how you move. So we've got an interface that says we're going to have different moving behaviors. They are implemented through a method called move, and then we have our concrete assets, our specific variants that we've built, moving with wings, moving with wheels, for instance. Each of those, the code is implemented in its own class, implementing that move method. Okay. Now in the robots, what we're going to do is we're going to state that there will be a move behavior and a shoot behavior. So two attributes, each storing a pointer to one of these concrete behaviors, one of these assets. So the robot doesn't change, but we could add more ways of moving and slot in a different version, or different ways of shooting and slot in a different version. Okay. All the children will inherit those attributes, and they can have a pointer to their own version of move, their own version of shoot. And we have a method in the robot that just delegates the method call out to the concrete moving or shooting behavior. So what we've done here is that we have separated what changes from what doesn't. Moving behavior is implemented separately from the robot in one place, and no matter what robot we're dealing with, we can access the right behavior in the right way and in the same way without needing to know which robot it is or which version of moving it is. So we get the right result. That's better design. This leads to a core principle of object-oriented design. Inheritance is useful. It's not always the right answer. Often we should favor composition over inheritance, constructing our own appropriate version of a robot from building blocks that do change. Right? A robot has a moving behavior, it has a shooting behavior, it has a targeting behavior. But instead of inheriting the moving or shooting from the parent class and making overrides, we have implemented behaviors once and composed new versions of a class from the right building blocks. We restrict a robot to what is true of all robots, right? And then we build a new robot from the right set of behaviors. This is the principle of composition. We build a class from small independent blocks, something we've repeated over and over when talking about product lines, right? Building from these independent pieces. Inheritance can be great, but only for those things that are actually shared. Composition is better for the aspects that can vary and that can change over time. So I have a moving behavior. I have a flying behavior. Or a moving behavior, a shooting behavior. That's better than I am I am a drone. I am a dog. Right? Now, those are some of the fundamental lessons of object-oriented development, but they could take some work to apply in practice. Unfortunately, we can learn from the experience of others. That's where design patterns are often incredibly useful. Don't start design by listing a set of classes, but start by describing a problem that you're addressing. And someone has probably addressed a similar problem before, or at least has learned similar lessons before about how we should design a system that's resilient to change, that's easy to change. And some of that experience has been summarized as what we call design patterns. These patterns serve as a reference guide for design for particular types of systems or development situations. They offer us some design guidelines. Now, each pattern, this is a nice quote from Christopher Alexander, the guy who popularized the concept of design patterns. He has a nice quote saying that every pattern describes a problem that occurs over and over again and the core of the solution, how you should approach solving that problem in a way that you can use the solution a million times over without doing it the same way twice. This really this quote really describes to me what a design pattern is. These patterns offer a head start to design. They offer the core of your solution. They're not libraries of code you plug in, right? A pattern doesn't give you something that you can just use from scratch and replace designing your own system, but they give you structure and guidance. They give you a set of instructions that will ideally result in a better design for your particular problem. Better support for customization, better support of expansion of our available options, better support for system evolution over time, right? And this is a pattern already, what's called the strategy pattern, where algorithms describe behaviors, and you take behaviors, you implement them as separate classes, and you make them interchangeable by ensuring they offer the same interface and just get plugged in at runtime. Even within one robot, we could swap one form of movement for another while we're running. We don't need to know which type of robot we're working with. We just know that if we call move, it moves. If we call shoot, it shoots. Call it as you would call any option, and it should work. And you can add in new assets. You could add new forms of movement, new forms of shooting, and new behaviors to that set over time and make use of them by binding the appropriate class at runtime. Now let's look at a second pattern. Right, a second pattern today is what we call the factory pattern. In manufacturing, you often end up building multiple versions of the same product. This motivation should sound familiar from our previous lectures, right? Say you're building a new laptop. Well, every laptop follows the same process, but the individual parts might be different RAM stacks, different hard drive capacities. You often see the same thing in restaurants, right? We might order, we might have a pizza restaurant. We could offer different pizzas with different toppings. Same process of initializing, building, delivering a pizza. But there are differences between the individual concrete pizzas we get back. Our pepperoni pizza is different from our sausage pizza or whatever. Well, these same situations, of course, happen in our code as well. And that's where the factory pattern comes in. It's a creational pattern that lets us exploit polymorphism to create the right type of object and change what types of options we offer for different objects without rewriting the code in several parts of the program. Okay, so let's say we've got our robots again, and our robots are part of a robot battle simulator. We can throw many types of robots into an arena and they fight each other. So setting up a fight triggers a sequence of events where we prepare our robot, we set its health, we set its ammunition, our loadout, and then we pop the bot into the arena to fight. Now, regardless of what robots we're going to have fight, the steps to set up the fight remain the same. We initialize a robot, we load its ammo, we set its armor, and we deploy it. Now, the specifics of what happens when you call those methods might be different for different robots. Some robots have different ammo, some have different armor, some have different initialization procedures, and so on. But we want the same sequence of events to occur for any robot. Now, there's something that's missing here, which is deciding on our type of robot. And as a first stab at this, we can add an argument for setting the robot type and use conditional statements to filter and instantiate the right type. Every type has to follow the robot interface and implement these preparation methods from our last slide, the load ammo, set armor, and so on. Okay, so we've got a sequence of if, else if, and so on. If we put an insect for our type string, we get an insect bot. If we use tank, we get a tank bot, and so on. Now, is this going to be a problem? Well, your set of robot models might not remain static, or you're going to add new robot types, or we might remove old ones, right? And this can be a problem, as this giant if statement we're building may not be entirely friendly to change, We might have to modify it over and over as our set of options changes, and this big if then else block might be plopped in many different places in our system. While the rest of this method, where we set up and deploy the robot, those might remain the same. And so this selection code isn't a design conducive to change. And really, this is a simple example. Often these bits of code are much more complicated. So again, what we want to do is take what does change and separate it from what doesn't. In this case, this instantiation code, we want to take it from every place it appears in the system, strip it out, and encapsulate the robot instantiation code into a special type of object that we call a factory. Factories can handle the details of object creation and often initialization as well. We might see this set of actions, initialize, load ammo, and so on as part of the factory as well. But as a simple point, the act of creating the right robot, we can delegate out to this robot factory. This gives us loose coupling. The deploy robot method just needs to know that it works with a robot. It doesn't need to know what kind of robot it's working with. It just cares that it gets a valid robot, which implements all the methods we expect a robot to implement. So the factory hands us the correct robot. We don't need to know what it is. We just get it back and work with it, and we prepare and deploy it. We don't need to know what type of robot it is, how it walks, what kind of gun it uses. We don't care. It just needs to act as we promised a robot will act, providing the right interface. Now, we're not quite to the full pattern yet. A couple more quirks we'll talk about, but here is a basic idea of what we want this robot arena to look like now that we've stripped out object creation and delegated it to the factory. Our robot arena contains a factory, which is called when we need to instantiate a robot. So we call the robot arena a client of our simple robot factory. We have several types of robot that all implement the same interface. And we still have this if statement I showed you before, but the important thing is when we have that list in one place. It's in our simple robot factory. It's in this create bot method, right? So it's in one place. If it ever needs to change, we change it in one place only. Thus, the factory can create any of the robot types, and the client knows how to use them and knows what a robot is, and it doesn't need to know what the specific robot is. So far, so good, right? But not all robots are the same. And maybe we eventually decide to introduce flying robots in addition to our previous land-based robots. So we might want to offer different hierarchies of options. We might want to let the user select a base robot type, land robot, flying robot, and then use different specific bots from each category. A drone from the flying category, a tank from the land category. In that case, we might not just want one robot factory, but we actually might want separate ones. For instance, some of the details of object creation might differ between land and robot. So we might want a land robot factory and a flying robot factory. So we can create sets of factories, each factory responsible for the creation of a subset of our items, our products. And that means that we want to create a factory interface and spin that off into concrete factories that offer the same contract to other methods. All of our robot factories offer this create robot method. Its internals might differ, but every factory is going to be accessed in the same way. You see this idea again, right? And each will be responsible for creating a subset of the robots. And from this, what we see is that we're really dealing in the factory pattern with two hierarchies of products and creators, both of which have interfaces. They have contracts that they agree to follow to present a common interface. All robots have the same methods. All robot factories have the same methods, but we have the creators and the products they create. Excuse me. So the factory pattern gives us a way to encapsulate the instantiations of concrete types. It lets us reason in terms of two parallel class hierarchies, creators and products. Factories encapsulate object creation, by letting subclasses decide which objects to create. All creators let us pass in options and use those to instantiate an object and pass the right object back. The objects we create, these products, may differ in the result of the methods they offer, but they all offer a common set of methods. So what does this look like in a more generic form? Well, we have a client who's concerned with both factories and products. For every product type we build, we have an interface that states the operations that can be assumed of that type of product. These do not have to be the same operations. We're just providing an interface for each type of product. So if we have flying robots and land robots, right? We have an interface that all land robots follow, and we have an interface that all flying robots follow. And these might not offer the same methods necessarily. Then we have concrete product classes for each type that implements those methods of the appropriate interface. A factory interface defines creation methods for each product type, right? So whether that's land robots, flying robots, and so on, each factory is responsible for creating certain subsets of our concrete products. Some might create a subset of all types of products. Others might only create one type of product, right? But each factory handles a subset of the products. So this gives us a few nice distinct benefits. And the first is that we preserve loose coupling. We can create and interact with objects without knowing exactly which concrete class we've instantiated. This is that programming to an interface rather than to an implementation. We know we have some land robots or some flying robots. We don't need to know whether it's a drone or a bird. We just know it's a flying robot. Second, creation code is centralized and making it easy to add or change our set of products. We can easily incorporate new types of robots. And that's that idea of encapsulating what changes and only changing it once. Same idea, different ways of realizing it in your system. And last, and very much related to the first point, if we put our creation code in our client, we have a high dependency in all the different product classes. You need to know which robot we're dealing with. We directly reference each product that can be created. We call their constructors directly. If we're using factories, we lower that class dependency and we can depend on abstractions and not concrete classes. Higher level components in our system should not depend on lower level components. Instead, sort of both sides of this should depend on abstractions and not need to know the details of each other, right? So our robot arena and a drone, they need to interact, but they don't really need to know more than what a robot is and how it can be interfaced with. Okay? All right, so now I'm getting tired. Let's talk about coffee. We have a coffee shop. Our coffee shop is updating the software for their ordering system. And they've set it up to be something a bit like this. They have a base beverage class with a description and an abstract cost method used to assess the bill. Then for each type of drink, we have a house blend of coffee, a dark roast, a decaf, and an espresso. And each of those implement a concrete cost method with an actual price. That's pretty reasonable, right? A lot of situations like this where we create our specialized children inherit base properties, fill in specifics. However, in addition to your coffee, you can also ask for condiments to be added, like milk, soy, mocha, whipped cream. And our coffee shop charges for each of those, so we need to be able to get the right total. So we're not just talking about a house blend. We might have a house blend with milk, with soy, with milk and mocha. If we decide that those are all special children in their own right with their own cost, we're going to run into trouble quickly. You're going to have a class explosion here, create a huge maintenance nightmare. What if the price of milk changes? Well, now we might have to update the price in dozens of places. What do we do if we had a new topping? Do we add dozens of new classes? That'd be an awful idea. Like, clearly this is a mistake. Clearly this is a bad way to approach this. And you do see designs that bad from time to time, but the point here is that people do over rely on inheritance. It's a powerful tool. It's more useful than you think from how much I've piled on it a little earlier, but people do misuse it. But now, when faced with this situation, a far more reasonable response is to use instance variables and inheritance to keep track of the condiments. So take two. Here's what we've got. We have Boolean values for each condiment. Okay. And instead of leaving cost abstract in the parent, we go ahead and calculate the cost for the condiments in the parent class. And then we add whatever the concrete amount is for this coffee. So for instance, for our house blend here, we call to the parent to get the price of whatever our condiments are. We get that back. We add 29 crowns for our house blend, and we return the total. That's far more reasonable, right? There might still be some issues here, but still, this is a much better starting place. The reason we use inheritance primarily is so that we can write code once. All the children just inherit that functionality. If we need to change that code later, we just need to make the changes to that parent, as long as the child doesn't override the method. That can be very useful, but it can still lead to designs that aren't easily maintainable or easily flexible like our original stab at the coffee store. When you inherit, all the children must inherit the same set of functions, the same set of variables. If you just want one function, that's too bad. You need to take it all, and that can lead to situations where you spend more time writing code to work around the behaviors you inherited and the side effects of that inheritance than you spent writing new functionality added to the child. As we saw with the robots and their targeting, their shooting, their flying, or their shooting, their movement, behaviors can be reused. They can be written once and changed in one place through composition. And that's where we're going here, is this composition. The idea of composition is that we can take pieces of the system, these assets, and we can use them as building blocks of something else. We can grab an object in the system and we can expand what it can do by attaching another object to it and calling into that attached object. We had that robot example before with the strategy pattern. We want to enable robots to move. Some robots move differently than others. Some might not move. Inheritance can't deal with that kind of situation easily. But we still only want to write our code once and reuse it. So we took those moving behaviors and we implemented them as their own class. Then we attached the appropriate wanted object creation. With inheritance, behaviors are passed statically. When we compile the code, every time we run it, the object will have the same features. With composition, we can attach objects at runtime. You can even change what features an object has as the system executes by changing the attached object. So you remember the robots again. We said each had a moving behavior as an attribute. Well, we could change what specific version of move behavior is attached while the system runs in response to the active events going on in the system. That makes sense? This is an incredibly powerful concept. It allows changes to a class while never changing the code of that class. You can add new functionality by writing new code in separate classes that we attach and call transparently. Because we don't have to change the existing code, our chances of introducing bugs are vastly reduced. And this introduces another fundamental principle of object-oriented design. What's the open-close principle, that classes should be open for extension and closed for modification. New features are great. We will eventually need them, so we want to add them. We want to evolve the system, but we spend a lot of time designing, testing, debugging the existing code, so we don't modify that. If it isn't broken, don't change it. Change will happen, but we can allow that to occur without directly modifying what we already have. Instead, take that unchanging class, attach it to a new class that builds in new data and operations. That new class can make use of anything in the class that it's holding, that it's attached to, and can add new features on top of that. Now, this is not something you want to apply everywhere. Following this principle means adding new levels of abstraction to the system, adding complexity to the code, But what you want to focus on are areas that are likely to evolve in the system, areas that are highly variable, that are customizable, and apply this principle there. So now how do we apply this in practice? Let's go back to our coffee shop, and we can introduce what's called the decorator pattern as a way to take a look at this idea. So with our coffee shop, inheritance doesn't solve our problem very elegantly. We can get some class explosion, right? Rigid designs, or we add new functionality to the base class that isn't appropriate for some of the subclasses. So what we want to do instead is start with our beverage and decorate it with condiments at runtime, adding them in. If the customer wants a dark roast with mocha and whipped cream, here's what we want to do. We start with our dark roast object. Now we're going to keep some level of inheritance in here. All of our base drinks will inherit from a class called beverage. So we can take advantage of polymorphism to maintain loose coupling. Our dark roast, our espresso, our house blend, those are all beverages. They inherit from the same parent. All right. The customer wants mocha in their dark roast. So what we can do is we can create a mocha object with a pointer and take that pointer and point it at our dark roast. So wrap it around our dark roast. The mocha object is what we call a decorator. Its type mirrors the object it wraps. So although conceptually mocha is a topping or a condiment, design-wise, it's going to inherit from beverage, and it's also going to have a cost method. This means that through polymorphism, any beverage wrapped in mocha is still a beverage because mocha is a subtype of beverage. And this maintains that loose coupling. Any beverage wrapped in a condiment is still a beverage, and the calling program doesn't need to know what specific beverage it is. It doesn't need to know it's a dark roast, and it doesn't need to know what kind of toppings it has. It doesn't need to know that it has mocha. We're still going to get the right cost back in the end. Now, the customer also wanted whipped cream, so we're going to also create our whip decorator and wrap the mocha with that. And again, our whipped cream is also considered a beverage. And it's got a pointer to the next layer, which is our mocha wrapped dark roast. Right? So we can keep wrapping endlessly around this. Now, it's time to compute a cost for the customer. And we do this by calling cost on the outermost decorator. The whipped cream delegates computing the cost to the object it decorates. Once it gets a cost, it will add that onto the cost of the whip. Then we call cost on whip, it calls cost on mocha, it calls cost on dark roast. Dark roast is our base layer. It returns the price to the mocha where it adds its additional fee, returns the new total. We add the additional fee from our final topping, returning the final total in the end. Make sense? So the decorator pattern attaches additional responsibilities to an object dynamically. This is a flexible alternative to inheritance when we want to add or we want to extend our functionality without modifying the code. Our decorators provide a flexible alternative to subclassing for extending our functionality. Our decorators have the same super type as the object they decorate, so we have a beverage in our coffee shop case. And given that use of polymorphism, by inheriting from the same super type, we can pass a decorated object in place of the original object. And that's the key point here. The decorator adds its own behavior. It adds its own functionality on top before or after asking the wrapped object to do the rest of the job. We get functionality from the wrapped objects. We perform any additional work that needs done without touching the code of that wrapped object. So what does this look like? Well, let's take a look here. Applying the decorator pattern is pretty simple. We've got two concepts: components, which get decorated, and decorators that wrap around a component. We deal with two levels of inheritance from the same base. So we've got a base component that all the concrete components are going to inherit from. This is like the beverage, and then the concrete below that are our house blend, espresso, dark roast. The components are what we dynamically add new behavior to. So we've got a base decorator that defines what decorators must offer. right? Since it inherits from the component, all decorators offer the same methods the components offer, in addition to anything they would add. Decorators contain an instance variable to store an object being decorated. That's how we keep track of what is being wrapped up here. When we can infinitely keep wrapping new decorators around an already decorated object, as long as we maintain a pointer to the next layer down until we reach the center. And decorators can also add new behavior by adding additional attributes and operations. That said, new behavior is typically added by doing computation before or after calling an existing method in the component, like we did with that cost in the previous slide. So let's revisit our coffee shop ordering system, this time with the decorator pattern. And here we've got our two levels of hierarchy. Types of coffee, and we have our condiments. And all these extend our beverage, okay? So we are going to have our decaf, our dark roast, our espresso, or house blend. These are all beverages implementing a cost method. And then we have our decorators. Our decorators have a pointer to the beverage they're decorating in their own cost method, right? And we have milk, soy, and mocha as our decorators. Now, within a decorator, our cost method is going to, first of all, go and get a total from whatever it's wrapped around, from the beverage it's wrapped around, and then add its own total on top. So our soy milk is going to add an extra 10 crowns to whatever it's wrapped around. And that can include, a house blend or an espresso, and then any number of condiments already. We could have double soy, right? We could wrap it in soy milk and then have an additional round of soy milk on top. And it's just going to get whatever's below it and add 10 crowns to that before returning the total. So the decorator pattern uses inheritance to achieve type matching, not to inherit behaviors. But really so that we can transparently treat all of these as the same data type. By composing a decorator with a component, we add new behavior. Composition adds flexibility to how we can mix and match behaviors. If we rely purely on inheritance, behavior is determined statically at compile time. We get only the behavior the superclass gives us or that we override. With composition, we can mix and match decorators in any way we like at runtime, just building on top of what's already there. We can add new behavior to our system by writing new decorators, or we could change existing decorators and change the price pretty easily in those. We can extend existing components without changing the underlying component. So the decorator pattern is very useful, but it does carry a couple of caveats to watch out for here. The decorator pattern often results in a very large number of small, simple classes, which can be a little messy in your design. It could give you a design that's harder to understand and find information in. So to take an example of this, there's Java's I/O library, which is implemented using the decorator pattern. When you're reading a file, you often open an input stream, wrap it in a file input stream, maybe wrap that in a buffered reader. That library is a little bit hard to understand until you start thinking of it as a decorator pattern, where you wrap additional functionality around an input stream. Right. Now, also, we can have some potential type issues here. If code doesn't need to know the specific type, decorators can be used transparently. Everything is a beverage. But if we need to know, for instance, specifically about a dark roast, like let's say a dark roast gets a discount, well, bad things happen once decorators are applied. It's really hard to figure that out concretely. So be a little careful in applying this. All right, now here's where we would normally be taking a break if this were in the lecture. But since we're not in the lecture, I'm going to continue. But if you're getting tired, maybe take a little bit of a break here. All right. Now, often we're in a situation where we want to bring in services or code from another system, maybe from an open source project, so we don't have to write it ourselves. However, the interface offered by that code may not match the one that your code is expecting. It's like trying to fit a square peg into a round hole, right? Your usual course of action would be to rewrite your code to work with the other system. But maybe that's not a great option either, because maybe that would require an extensive overhaul of your code base. Let's say that this is a point where we have all of our different robots and we're importing someone else's robot code. We don't want to change all of our existing robots to match that one robot's interface. That might not really be something we can or want to do. So what can we do about this instead then? Or here's a real world analog. Let's say that you've traveled to the United States from Sweden and you pull out your laptop charger and it doesn't fit in the outlet. Different countries, different standards for how you convey electricity. You're not just going to shove it in the wall. What you do is you get an adapter, right? You plug your American charger into one end, plug the other end into the European outlet, and bam, it all works, right? Some adapters are simple. They just change the shape of your plug. Others are far more complex. They convert one voltage type to another. The idea is the same, though. Plug one version into one end, get the version you want, continue working with it. You don't want to change the outlet, and you don't want to change the original plug, but something in between the two to make them work well together. And we want to do the same thing with our software. We don't want to change our code. Maybe we can't change the external code. So we write a class that sits between the two and performs translation for us. It turns the adapted interface into the one that we expect. The adapter implements the interface your code expects and talks to the vendor, the external code's interface, to serve requests. It acts as a middleman, a piece of new code that enables you to use your existing system and this external code without making any changes to what you already have. And this should sound a little familiar from what we just talked about with the decorator pattern, where you wrap classes to add new functionality. The adapter pattern is another case of a wrapper. It wraps classes in a similar manner to change how you access the existing functionality. It wraps an interface around an object to change how we call its underlying functions. And this is basically a special case of decorator where we don't add behavior generally, but we just translate how we access existing behaviors. So we're back to our robots we had at the start. And we had a robot interface that says all robots move and shoot. We want to be able to add new types of robots. And we've got some code available for some unarmed exploration drones, these things that can survey and look at environments. They don't fight, though. They don't shoot. And that'll do the trick. Maybe that's something we could use to extend our system, but they're not quite the same as the robots we have already. They don't shoot, they inspect objects. So they're similar, they don't quite offer the same interface. We might not be able to rewrite that drone code either, right? They might just come in as objects from an imported library. And we might not want to rewrite our robots either. They still don't inspect things, but we can write the adapter that maps the two. So a robot adapter implements the interface of the type we're adapting to. It stores a reference to the object we're adapting. And then we implement the methods in the interface, translating to the versions we want to access in the adaptee class. In this case is very easy, right? Our shoot method is just going to call inspect. Move is going to call move, right? But now everything from this library is going to be able to be interacted with in the same way through this adapter. Okay, this is a similar idea again to the decorator pattern. We just take an existing class, we wrap an adapter around it, we modify its functionality to be compatible with our system and its needs. So the adapter pattern converts the interface of a class into the interface the client expects. The adapters let classes work together despite incompatible interfaces. That pattern allows us to use a client with an incompatible interface by creating an adapter that does that conversion. And this acts to decouple the client from the implemented interface. And if that interface ends up changing over time, the adapter encapsulates that change so that the client doesn't need to be modified every time it needs to operate against a different interface. This is a big deal for code reuse. It allows us to build a system out of independent external code far more easily. Now, that example had the adapter wrapped around one adaptee. The underwater exploration drone was adapted to match the interface of a robot. And here's what this pattern looks like in the abstract, right? We've got a client. Our client only sees this target interface. It knows about robots. It doesn't need to know about underwater exploration drones. Our adapter is going to implement that target interface. This is what we're translating into. Our adapter has a pointer to the adaptee. It's composed with the adaptee, and it's going to offer the methods of the interface it's implementing. Those methods will concretely translate to methods calls in the adaptee. So requests get called into the adaptee through this translation. There's a lot of good object-oriented principles at work here. We use object composition to wrap the adaptee with an altered interface. We can even use the adapter with any subclass of the adaptee, and this pattern binds the client to an interface, not to a particular implementation. Again, our client is in our robot example, knows about robots. It doesn't know about underwater exploration drones. It just knows about robots, right? Not to a particular implementation. We could even write several situationally appropriate adapters converting a different backend set of classes. Now let's look at another different but related situation. And let's say we're going to go watch a movie, right? And we've got a few simple tasks we're going to perform to watch our movie. We're going to, start popping some popcorn. We're going to dim the lights. We'll pull down the screen, turn on our projector, set it to Blu-ray mode, turn on our sound amplifier, set it to the right inputs, turn on our surround sound. We're going to turn on our Blu-ray player, start the movie. Us simple people with our 13 steps to watch a movie. All right, well, this is obviously a lot of work. It involves interacting with 6 different devices here. And it doesn't end here. When the movie is over, how do we turn everything off at the end? Do we do the same steps in reverse? Would it be as complex as to listen to Spotify or the radio? If we upgrade this system, would we need to learn a different startup procedure? This is a little convoluted. Let's make this a little simpler. Well, we've talked already about wrapping classes, about this idea of decoration, where the adapter pattern converts the interface of a class into one that the client is expecting. The decorator pattern doesn't alter any interfaces, but it wraps classes and new functionality on top of what they already do. Well, we've got a third pattern now, closely related, that can help with this sort of situation. It's called the facade pattern. The facade pattern simplifies interactions by hiding complexity behind a clean, easy to understand interface. The point of this pattern is to wrap a set of classes into one shared interface. So what we want to do is create a new class, our home theater facade, and it's just going to enable and expose a few simple methods. Things like start movie or start Spotify, end movie, end Spotify. Very high level pieces of functionality that we might want to perform very often. But rather than making a series of 13 method calls, we instead make one method call that triggers those 13 actions. So the facade treats these different home theater components as a black box. They can do many things, these classes, for our Blu-ray player, for our lights, for our projector. There's a lot they can do, but we want to hide some of that complexity behind this simple interface that offers simple, repeatable actions over and over again. And we call on the subsystem to implement those methods. So rather than including that whole sequence of commands to start a movie, we're going to take those, we're going to implement them in a single method in the facade and never have to go through that whole sequence again when using the system later. Just call that method instead. So a client code calls methods of the facade instead of working deeply with the individual subsystem classes. This acts as an interface into part of our system, where we no longer have to communicate directly with the lights, or the amplifier and so on, but we communicate through that facade instead. This reduces our coupling on the individual classes of the system. Now, those classes are there if we need them in our system. We can still work directly with the Blu-ray player, work directly with the stereo if we need that advanced functionality. But what this does is it simplifies our interactions with that code the rest of the time. It decouples that subsystem, those different home theater components, from the client, from the calling code. And this eases the ability to change. It means that if we get rid of a Blu-ray player and just use streaming media, for example, well, in our client code that calls into that, we don't need to know that it's a Blu-ray player. We don't need to know that it's Netflix. We don't need to know that it's Disney Plus and so on, right? We just call this start movie method and it works. It makes it easier to change classes underlying the facade. It makes it easier to swap classes out without having to know about those changes in the client code working with this facade. So the facade pattern provides a unified interface to a set of classes in a subsystem. It defines a higher level interface that makes the subsystem, those collected set of classes, easier to use and interact with. There's no direct encapsulation going on here. Instead, we're actually just offering one more method of access, a simpler method of access. And that's a nice property of the facade pattern, actually. Rather than stripping this code out and throwing it somewhere where we can't really work with it closely, it's still there if we need it. We're just providing an additional simplified interface while still exposing the full functionality of the system to those clients who need it. Multiple facades can be defined for the same subsystem, the same set of classes, even to provide different situational functions. This decouples the client from any one single subsystem. Let's say that you add a new home theater component. You just need to change the facade rather than the code in that client system. So in terms of a class diagram, this is as simple as it gets. A client is working with a facade. The facade acts as a layer between the client and a potentially complicated web of subsystem classes. There's not much more to it than that, but the idea is really powerful. This is an idea you should remember. It tells us loud and clear the intent of this pattern. We want to put a simplified, changeable interface between client code and this complex, highly coupled set of classes. This leads us to another really important design idea. We call this principle of least knowledge, talking only to your immediate friends. In your code, you want to reduce as much as you can the number of interactions that take place between different objects when possible. When you're designing a class, you want to be careful of the number of other classes it interacts with and how it interacts with them. Because every time you change either your class or these other classes, you might have to make changes that spill through your system, right, into all the dependencies. We want to avoid creating designs where the objects are highly coupled together. That makes it hard to change, evolve a system, and to add new options or to change existing options. When you have a lot of dependencies, you're building a fragile system that will be expensive to maintain, that will be complex for others to understand. We want to only invoke methods that belong to the object itself, to objects that are passed in as parameters, to objects a method creates and instantiates, and components of the object, the things that we have a pointer to. The facade pattern maintains this idea by ensuring that the client only has one friend, that facade. We only work with the facade. We don't work with the classes underlying that facade. One friend is a good thing. Well, that sounds lonely, doesn't it? And anyway, the facade keeps the client simple and flexible by managing the subsystem components for the client. It adds in this simple interface layer. and we only need to worry about understanding what that interface offers. We can upgrade the home theater. We can change how Blu-rays are played, for instance, without upgrading that code in the client that does things with that theater, like watching the Blu-rays. All right, one more pattern for us here. A little earlier, we talked an awful lot about our coffee shop. And, some of us can't live without our coffee, or today I'm drinking a Coke. Pepsi if we want to be technical, but I'm not sponsored. Can't sponsor me if you want. Okay, anyway, some of us can't live without our coffee. Some of us are tea maniacs instead. And as it turns out, coffee and tea are made in a very similar way, right? For the coffee, we're boiling some water, brewing the coffee in that water, pouring it in the cup, add sugar and milk if we want. For our tea, we're going to boil some water. We're going to steep that tea in the boiling water, going to pour it in the cup. Maybe we'll add lemon, right? Or sugar or milk again. But you see that these look pretty similar, don't they? And let's say that we're, building code for our for our beverage maker, something that can make coffee and tea. And this is what this might look like within our code, right? Our coffee and tea classes, our coffee, both have a prepare recipe method that encapsulates the series of steps to create the beverage. So we boil our water, brew the coffee, pour in the cup, add toppings. For our tea, we're going to boil water, steep our tea, pour it in the cup, add lemon. Okay. Now, again, we're seeing these processes look very similar. It's basically the same recipe. And so we probably have some code duplication going on here. And when we have duplication, so boiling water, pouring in a cup, for instance, that's a good sign that we need to clean up our design a little bit. We want to have that code, again, once and reusable. So our first inclination, right, is that we should take these common steps and abstract them into a base class and inherit those common steps. So our first redesign might look a little bit like this. Boil water and pour in cup are common, so they're in this base caffeinated beverage class. And we're going to declare an abstract method called prepare recipe that each child is going to concretely implement, in addition to any new behaviors unique to those children, like brew coffee grinds versus steeping the tea bag. All right, so, this is a little better. But we might be overlooking some other commonality here. Maybe there's some other ways that coffee and tea are similar that we can take advantage of. So what else do coffee and tea have in common? Well, let's look at their recipes again. Both recipes follow essentially the same algorithm. Boil some water, use the hot water we boiled to extract the beverage from a solid form, from our tea leaves or from our coffee grounds, pour it into the cup, add some kind of appropriate beverage. And well, two of those steps 1 and 3 here, are already abstracted into our base class. Steps 2 and 4 are not, but they're still essentially the same concept being applied to different beverages, with maybe some differences in the concrete form between the two. So, can we find a way to abstract this prepare recipe method as well? Right? So for our coffee, we have brew coffee grinds, add sugar and milk. For our tea, steep tea bag, and add lemon. These aren't really all that different. These are really just brewing something and adding different toppings, well, those adding toppings no matter what. So what we really have here is the same process. We have this new prepare recipe method with our 4 steps: boil water, brew something, pour it in the cup, add condiments. Make this a little more reusable in general. Okay, so let's redesign our code a little bit. We've got our caffeine beverage here with this prepare recipe method, and it's got these 4 steps: boil water, brew, pour in cup, add condiments. 2 of these are shared: boil water and pour in a cup. Those are the same for both tea and coffee, so those are implemented in the parent. But we've now declared these 2 abstract methods: brew and add condiments. These will be handled concretely in the children. right? And they'll differ between the children, so they're declared as abstract methods. But what we have done here is that we have one standard prepare recipe method with a standard set of steps, and we're delegating out what does differ to the children. But in the parent, we have so much here now that is concrete, that doesn't change, okay? So we need to deal with the coffee and tea classes, and they now rely on caffeine beverage to handle the recipe. They just need to handle the differing parts, the brewing and the condiments. So what have we really done here, right? Well, we've recognized that two recipes are essentially the same, although some of the steps require different implementations. So we've generalized the recipe and we placed it in a base class. Caffeine beverage knows and it controls the steps of the recipe. It performs the common steps itself. So we've encapsulated what does not change and rely on the subclass to implement the unique steps, what does change. And this is what's known as the template method pattern. This is a design pattern where we have some kind of shared process, some kind of shared algorithm. In this case, we have this prepare recipe. This is what we call our template method. It's a method that serves as a template for performing a repeatable algorithm, repeatable process. In our case, this is a repeatable process for making caffeinated beverages. But in the template, every step of the algorithm is represented by a method. Every step of this process is a method call. Some of these methods are handled in the base class by the parent. Others are declared as abstract and handled by subclasses that we plug in. The template method defines the steps of a process and allows subclasses to provide concrete implementations for one or more of the individual steps, while the shared steps are implemented in the parent. So why? What does this do for us? Well, in our original, the coffee and the tea are in charge of this process. We have duplicate code. And if we want to make a change to the process, that requires every subclass potentially be redesigned to follow the same mapping. Our classes are organized in the structure where if we want to add an additional beverage, now we need to do some work potentially to every single beverage as well. Like if we add soda to this, or if we add some other hot beverage, so if we add I don't know, some kind of hot chocolate to this, well, we might also have to change coffee and tea so that all of these beverages are mapped together. Instead, here it's a little bit different, right? Here, the caffeine beverage controls and protects the process of creating the beverage. It implements that common code. So this parent presents this core, unchanging basis. All the knowledge that we need to understand of how to brew a beverage is in the parent. The algorithm, the process, it lives in the parent. If we make changes to the process, the changes are made there, right? We only need to look at the children, at the concrete beverages for specific individual steps. If we add a new beverage, if we add our hot chocolate, well, we don't have to change anything in coffee or tea. We only need to implement new concrete steps in hot chocolate and maybe make some changes to our algorithm if necessary in the parent, in caffeine beverage. Caffeine beverage contains and controls all of our knowledge about this process, right? And we only need to look at coffee, tea, hot chocolate if we need that specific information on the implementation of those steps. That's a very powerful way to enable an evolvable design. The template method pattern defines the skeleton of an algorithm in a method, deferring some steps to the subclasses. The template method lets subclasses redefine certain steps of an algorithm without changing the algorithm's overall structure. So our template is a method that defines an algorithm as a set of steps, where each step is a method call. Abstract steps are implemented by subclasses. This ensures the algorithm structure stays unchanged. Again, providing encapsulation for what does not change and letting you append what does change in subclasses that provide part of the implementation. So abstractly here, We have a class that contains the template method and abstract versions of concrete operations used. Okay. We've got concrete classes that can implement one or more of these primitive operations required by the template method. And the template method makes use of these primitive operations to implement the algorithm. They're decoupled from the actual implementation of these operations. So if we dive into the code of this, right? We've got our abstract class that controls the process. It's declared abstract because we don't call caffeine beverage directly. We work with coffee, we work with tea, we work with hot chocolate, right? But they all share the same data type. They're all going to be able to call the template method and work through this set of steps. We're going to inherit certain operations. We might have some concrete operations, but some of these might remain abstract in the original parent class and be implemented concretely in the children. Okay. We're going to declare the template method final to prevent our subclasses from changing the sequence of operations. The parent should define the sequence of operations. And each of those, again, is a method we call. Now, the parent class can define concrete methods that are empty or have a default implementation also. We call these hooks, where subclasses can selectively override them but don't have to. This gives subclasses the ability to hook into the algorithm if they wish. We've added a little conditional statement into the recipe that bases its success on a concrete method. So for instance, in here, if we want condiments, we're going to add them selectively. And by default, that's true. Now in the child class, what we're going to do is you're going to get an answer back for yes, we do, or yes, we don't. So if a customer wants a condiment, only then do we add condiments. We defined a method with a mostly empty default implementation here. We just return true. And this is our hook because the subclass can override it, but it doesn't have to. For instance, our tea might just take this and say true and add those condiments. But in our coffee class, well, we go out and ask them, right? We have a slightly more complicated version of this. Through this additional method, it's not necessarily part of our core algorithm. Now, as it turns out, we've got another nice design principle at play in the template method pattern. It's what we call this Hollywood principle. Don't call us, we'll call you. What does this have to do with object-oriented development? Well, it prevents what we call dependency rot. When high-level components depend on low-level components, and similarly, the low-level components depend at the same time on the high-level components. We got this cycle between the high and the low level. When you have dependency rot, it's hard to understand how a system is designed. The knowledge of how it works is split. For instance, between the hot beverage, coffee, and tea, we'd have to understand all of them together without this pattern. This principle allows low-level components to hook into a system and work with them, but the high-level components decide when and how they're needed. The caffeine beverage class, or hot beverage class, whatever I called it in the last couple of slides, controls the algorithm, right? It controls the process. It tells us what we need to understand. We only work with the low-level components when we need them, and they don't have to call into the higher level components. When we design with the template method, we're telling those subclasses, you don't call us. There's no calls back into hot beverage from coffee or tea. Our hot beverage has control over the algorithm. It calls the subclasses only when they're needed for an implementation of a method. The low-level subclasses are used simply to provide implementation details. Okay, so these patterns capture several really important design principles that allow evolution, that allow variability of a system without increasing our complexity. The first, and this is the big thing, is that we can identify aspects of our system that vary and encapsulate them, keep them away from what doesn't change, what doesn't vary. This is the big one. This is what almost all of our object-oriented design is based on. Take the parts of the program that will change, separate them as much as possible from what doesn't change much. Keep them loosely coupled, then changes won't wreck your system. Second is programming to an interface rather than an implementation. If you plan to have multiple objects that are similar but vary little in their details, either design a superclass or an interface that all the specialized child classes adhere to. If you're designing a system with many different robot types, ensure that they all offer the same types of operations using the same style of invocation, the same method names. Even if they make different, use different guns or move in different ways, make them all shoot or move using the same interface, the same method names. That way, we can design a system, to not require knowledge of the individual types. Third, favor composition over inheritance. Although inheritance is a powerful feature, passing a type and a set of methods, it can be rigid. The children must accept all functionality passed from the parent, and the abilities passed along are determined statically at compile time. By using composition to build a class, we can dynamically extend the abilities of an object at runtime by attaching other objects to it. We can still write functionality once and change it once, but without the rigidity of inheritance. Fourth, you should be open for extension but closed for modification. This open-closed principle. We want to be able to extend the abilities of a class in the future, but we want to do so as much as possible without having to alter the existing code. The existing code has been debugged, and if we have to rewrite it to add new functionality, then we're probably going to add new bugs into our code that we thought was working. Fifth, talk only to your immediate friends. When you're designing a class, be careful of the number of dependencies it has in other classes, how it interacts with other classes. Avoid strict coupling. Avoid situations where if you have to change one class, you must change the other as well. And finally, don't call us, we'll call you. You shouldn't have cyclical calls between different components, cyclical dependencies. Low-level components should be usable by a system called from high-level components, but those low-level components shouldn't be calling back into the high-level components. Now, design patterns aren't a magic bullet. You don't necessarily want to just plug one in, compile, go out for coffee, etc. You need to consider the consequences of patterns on your design, right? They can lead to complex or over-engineered solutions. They can increase your system complexity, and they can lead to very inefficient designs. So be careful when you're applying. Consider whether they actually make sense. Don't overcomplicate your design when a simpler solution will work, but do what you can to ensure that your system can evolve over time and can be maintained over time. Okay, so let's wrap up a little. Design patterns are a really, really incredibly powerful tool, and I know you've talked about them some in previous classes, but it's a good reminder here that design patterns allow management of variability in code. They take these principles of object-oriented development and show us how to realize them in our software, right? Now, some that are very suitable to customizable or variable systems include the strategy pattern, where interchangeable behaviors are defined in their own classes, and we delegate to those classes how a behavior is performed. The factory pattern allows us to encapsulate object creation and initialization so that we don't need to know what type of object was created. We just need to know that we can work with it. The decorator pattern wraps additional behavior around existing objects so that we can implement changes in these wrappers and leave the original code alone. The adapter pattern also wraps objects, but it changes how we call them. It offers a translation so that we can take previously unrelated objects and treat them as a part of a growing set in our system. The facade pattern also wraps a set of classes, but it wraps them in a simplified interface so that we don't need to know all the low-level details of their implementation. And the template method pattern also lets us encapsulate an algorithm in one place and call into concrete implementations of certain steps of the algorithm so that we have these subclasses that we can use without without needing to know all details of them and without them being accessing the higher level. Okay, great. Well, that's all I've got for you today. Next class, we'll continue talking about modularity and design for variable systems. Assignment 2 is, of course, in progress. Please let us know if you have any questions on the assignment or this content in the next lecture, or of course, you can email anytime. I hope the career fair is going well. Best of luck in getting jobs, and let us know if we can do anything.